For my third course overview problem, I thought I'd combine the subject of waves, moment of inertia, and energy. Waves is the last thing we did in this course. So let's suppose that you have a flagpole that's on top of a really tall skyscraper. There's no way to measure its mass because it's up there. But what you can do, I guess, is go to that floor where the flag is, open the window, and just pay attention to what you're hearing. Because the skyscraper is so high up in the air, let's suppose that there's a strong wind blowing, and that wind can then set the wave into the cable attaching the flagpole to the building into some sort of a vibration, and you can hear the frequency of sound. You can also observe visually the nature of vibration by looking at the cable yourself. So let's suppose that you look at this cable and you find that you see this pattern of standing waves. So there are two nodes in the middle. So this would be the case of n equals 3, because the number of antinodes is what gives us the mode number of vibration. So that's the n equals 3 vibration, and let's suppose you're hearing a frequency that I give f. You use your cell phone app that measures frequency, and you find that the frequency you hear is f. So that's what you know. Okay. From that, can you find the mass of the flagpole? Is the question. So that's the first part of the question. Then what happens is something happens. Some bird comes and pecks really hard at this cable. Say it's got a beak of steel, so it cuts the cable. And now we're going to ask the next follow-up question to that is, with what speed does the rod hit the wall of the skyscraper? So that's our two-part problem. Part 1, you have the frequency. From that, can you find the mass? And part 2, if the cable breaks, find the final angular speed omega f when it hits the wall of the building. So that's a nice two-part problem. Let's try to see if we can solve it. Let's start by drawing a free body diagram for this flagpole. There's going to be some horizontal and vertical components of the hinge force. I'm not too interested in them, so I'll take my pivot to be the point of torque. There's going to be the tension of the cable, F sub T. Let's assume that you have given here the mass per unit length of the cable, which remember we call mu. And you're also given the attachment point to be 2/3 of the length. So you start from here and go 2/3 of the length of the flagpole out, and that's where the cable is attached. And the length of the flagpole is L, and the mass of the flagpole, of course, we need to find out what it is. 30-degree angle is the angle made between the flagpole and the horizontal. We have to work this problem backwards. So first of all, because it's a uniform rod, the weight of the rod is going to go right through. From the theory of vibration, from standing wave theory, we can write down the relationship between frequency and wavelength. Frequency times wavelength is equal to the speed of sound in the cable, and the speed of sound in the cable, Vs, is given by the square root of the tension in the cable divided by the mass per unit length of the cable. I'm assuming that the mass per unit length is given, and the tension we now need to find. Okay, so from here we can find the tension. Let's do that. Lambda here is 1/2 of a lambda. These melons, standing wave melons, are each worth half a lambda. So 1/2 of a lambda times 3, or 3/2 of a lambda, equal to the length of the cable. So let's write that down. 3/2 lambda equals cable length the length of the cable is going to be 2/3 L times cosine theta. 2/3 L being the attachment point, and that's the cosine theta component, that would be the length. So we have that, so we know lambda now. Lambda is going to be 4/9 L cosine theta. I'll keep cosine theta as it is and then put the numbers at the end. So F times lambda, if I square both sides, I'm going to get F squared lambda squared equals Ft over mu. So from this equation, I'm going to get Ft equals mu times F squared times lambda squared. Well, that's a further square of 4/9, and so that's 1681 L squared cosine squared theta. Impressive looking thing. So let's put the value of cosine theta here. Cosine theta is √3/2 for 30 degrees. So cosine squared theta is just 3/4. So that gives me 4 divided by 27 mu F squared L squared. I should have called that L. I'm just going to call this L, script L, because I've written that everywhere. All right. That's the tension. Now we can look at the statics problem. The statics problem, that's part 1. Part 2 is the statics problem. That tells you the sum of all the torques about the pivot equals 0. Choosing the pivot as your point to take the torque means that you don't have to worry about F sub V and F sub H, and you just have to think about mg and F sub T. Now mg contributes a negative torque because it's going to go in the counterclockwise direction, and clockwise direction is positive. So tension is going to contribute a positive torque. So that's going to be negative mg times this distance, which is L/2 cosine 30 degrees. Positive Ft times 2/3 L times sine theta, which is again 30 degrees. And that's equal to 0. Very nice. You notice that L cancels out here. I can put for Ft this thing. So I have, let's do the following. I'll take mg over 2 cosine theta to the other side. Let me just do this here. Mg over 2 cosine theta, cosine 30, equals 2/3 Ft sine 30. That tells me that m equals 4/3 Ft over g tan 30 degrees. So I have the mass of the flagpole. 4/3 times 4/27 mu F squared L squared divided by g. Now sine 30 is half cosine 30, so that's tan 30 is 1/√3. So this is what I have for the mass of this object. So we have done the first part of the problem. So that's 16 over, back to 16 over 81 √3 mu F squared L squared over g. Pretty impressive. Just by using your cell phone app, and assuming the cable is standard flagpole cable, so you can look up its mu online, and then this F is what you measure in your app, L is either what you estimate by looking at the flagpole, or someone tells you these flagpoles are 15 feet long or something, and G is 9.8. So from that you can simply get the mass of the flagpole without ever taking it off the hinge and putting it on a scale. So that's pretty neat. The last thing we need to do is calculate what happens when the really strong bird pecks the cable and causes this thing to fall. So here, what's going to happen at this point is that the potential energy that this rod had will be completely transformed into, the loss of potential energy will be transformed into rotational kinetic energy. The loss of potential energy is the following. This is going to be L over 2, okay, because the center of gravity of the rod is going to be this way, all the way down. And this part, well, that's L over 2 sine theta, or sine 30 degrees, which is half. So that's L over 4. L over 4 plus L over 2 is the total loss of potential energy, total loss of height. So the loss of potential energy must be equal to the gain in rotational kinetic energy about the pivot P. That's our technique. So I'll write this as the mass of the rod times G times 3/4 L, and the rotational kinetic energy gain is 1/2 the moment of inertia of the rod about the pivot point, omega final squared. We are done. I just have to put some torque values here. The moment of inertia of a rod pivoted about one end is found in your table of moment of inertia. It's 1/3 ml squared times omega f squared. The mass cancels out. How nice. So this part is kind of independent of the previous part. You could have found this without even finding the mass of the rod. So I have that. I don't think I can do any. Oh, I can take this 2. And then I have 9 over 2. So omega f squared equals 9 over 2 g over L. That's a very nice thing to have dimensionally, because g has got units of meters per second squared and L has got units of meters. So when you take g over L, you're going to get units of 1 over second squared, which you can write as radians squared over second squared, because radians is really what it is a ratio of the circumference to the diameter of a circle. So really you don't care about radians. You can bring it in when you need it and throw it out when you don't need it. In this case I need it, so I bring it in. When I take the square root, I get radians per second, which is what I need. So omega final equals 4.5 g over L square root. So I've answered both parts of the question. I found the mass of the flagpole in terms of the frequency, the length of the flagpole, and the mass per unit length of the cable. And I found the final angular velocity of the flagpole when it hits the building to be that. So I've completely solved the problem.